Okay, so we will continue with beta decay. Last lecture we have discussed the alpha decay, so now we are going to discuss the beta decay. So the beta decay basically can be categorized into three types. First one is beta minus decay, or also called negative electron emission decay. The second type is the beta plus decay, which also called positive electron emission decay, and the last one is electron capture. So next we will see that in the decay process the number of proton, electron and neutrons are conserved, and the energy is conserved as well. So we start with beta minus decay. Right, so beta minus decay, or the negative electron emission decay. So as usual, we begin with the parent nuclide X A Z N, and what we'll get is what we will get are the daughter nuclide plus one negative electron, or exactly the electron, and one a type of elementary particle called antineutrino. Okay, so the correct way to represent the antineutrino is, first you write nu, E and bar at the top. So this is now complete. You still have mass number A, the same mass number A, but increase number of proton and decrease number of neutron, right? And this is called antineutrino. Antineutrino. So antineutrino is a type of elementary particle. As opposed to antineutrino, we have neutrino. We will see that later. So in beta minus decay, what is actually happen is that the neutron in the parent nuclide transform to a proton, and at the same time releasing an electron and an antineutrino. Okay, so beginning with the parent nuclide, we have the daughter nuclide with one electron and an antineutrino. So the neutron in the parent nucleus transform to protons, and at the same time releasing an electron and an antineutrino. Okay. Now we have to analyze the conservation of energy in the beta minus decay process. Okay, the energy is so prior to the decay, we only have the mass energy of the parent nuclide square, and after the decay we have the of course I forgot to mention that since the daughter nuclide is now has excessive 1 proton, so it is positively charged, and usually it is at an excited state, so I put asterisk here. Okay, so continue with the conservation of energy. So this is before the decay and after the decay. We got the mass energy for the daughter nuclide, Az plus 1 and minus 1 C square, and minus 1 electron. Okay, so you see, to have this state, you have to remove 1 electron, right? So and this is for the daughter nuclei, and next we have the release mass energy for the release electron. So m e c square, and then the kinetic energy of the electron and kinetic energy of the antineutrino. So here we are neglecting the mass energy of the antineutrino, because the mass of antineutrino is far smaller than the mass of an electron. So here you can see that the mass energy of electrons are cancelled, and finally we have the Q value for our beta minus decay, which is equal to the kinetic energy of the released electron plus the kinetic energy of the released antineutrino, which is exactly equal to the mass energy of the parent nuclide and minus the mass energy of the daughter nuclide. Mz A Z plus 1 and minus 1, and don't forget the C square. I have no space to write the C square, so I write it here. Okay, so we are neglecting the binding, the mass energy for the antineutrino. So please note that the beta minus decay occurs at the neutron rich nuclide. Okay, neutron rich nuclide. So because there are massive, the number of neutron are so large, the number has to be reduced. So the way to reduce it is by change the neutron to a proton. So next we already had the beta minus decay, so next is the beta plus decay. So beta plus decay is also known as the positive electron emission decay. So just now in the beta minus decay, negative electron, or exactly an electron, is released, but in the beta plus decay, the positively charged electron is released. Okay, and as opposed to the beta minus decay, beta plus decay occurs at the neutron deficient nuclides. Neutron deficient nuclides. So nuclides that are lack of neutrons will undergo the beta plus decay. So as usual, we begin with the parent nuclides, parent nucleus. So AZN change to the daughter. Sorry, I use Z as the symbol for the daughter nuclide. Don't get confused, because it is the same. You can use any symbol you want. And during the explanation for alpha decay, I use Y. Okay, so the concept is still the same, just the symbol is changed. So now I use Z for the daughter nuclide. So Z still have the same mass number, but the proton is decreased by 1. Okay, decreased by 1, and neutron increase by 1, right? So the daughter is at an excited state, and because here we lack of 1 protons, automatically the atom is negatively in charge. Okay, so when the beta plus decay occur, it will release 1 positively charged electron. So during the beta plus decay, a positively charged electron or positron and a neutrino are released. So this is neutrino. Okay, so what actually happened is that the proton inside the parent nucleus transform to a neutron, and at the same time creating a positron and a neutrino. Okay, so because the parent nuclides are deficient in neutron, so it has to increase the number of neutron by sacrificing its proton. Okay, so now these are the process, and next is the conservation of energy. So at the beginning we have the mass energy of the parent, and next we have the mass energy for the daughter. So this is A, Z minus 1 and plus 1. Of course, it's still at an excited state, plus the mass energy for this electron is square. Okay, so to have this state, you have to add 1 electron. Okay, 1 electron, you add 1 electron to this nuclide to have this state. Okay, And next is the mass energy for the release, the emitted electron. The emitted positron, okay, so I put plus sign here, c square, and then kinetic energy of the release positron, kinetic energy for the release neutrino, and that's all the energy we have. And we like in the beta minus decay, we are neglecting the mass energy for the neutrino, and as well as the binding energy of this release positron. Okay, and now keep in mind that the mass for the positron is exactly the same as the electron, and the only difference is they are charged. Okay, so these two can be combined together, so eventually we will get the Q value for the beta plus decay, which is the kinetic energy of the positron plus the kinetic energy of the neutrino, which is exactly the mass energy of the parent minus the daughter, c minus 1 and plus 1. I'm sorry, it is so messy. And don't forget the mass energy of these two electron, okay, is c square, 2me c square, okay, 2me for these two electron and positron. So note here that m e is equal to m e plus. Okay, all right. Okay, still at the excited. So next we are going to look at the electron capture, okay, which is one of the category of beta decay. And like the beta plus decay, the electron capture also occurs at the neutron division nuclides. So electron capture, okay. So in the electron capture, the parent nucleus is actually capturing an electron from, this is the electron from the K shell. So one of the K shell electron is pulled into the nucleus, okay, and resulting daughter nuclide, same mass number, but increase one neutron, decrease one proton, of course, as usual as at excited states, and a neutrino is too big. and a neutrino. Okay, I should use Z, not Y. Z as the daughter nuclide. Okay, so what actually happening inside the parent nucleus is that the proton, so the parent nucleus is lack of neutron, so the proton combined with electron from the K shell form a neutron and a neutrino. So because the nucleus is lack of neutron, so it has to find a way to increase the number of neutron by sacrificing one proton and pulling in one electron from the K shell. So as the result, the number of proton is decreased and number of neutron is increased by 1. And that is that. So the Q value for the electron capture, I use this symbol, is equal to we only have the kinetic energy. Okay, we will have I'm sorry, it's not yet the Q value. We have to balance the energy first. So before the decay, we have the mass energy of the parent plus which is equal, we don't have to consider the mass energy of this electron, because this electron is exactly come from the parent atom. Okay, so it is not from the outside, it's from the inside the atom itself. So we don't have to consider the mass energy of this electron. So this is before the decay, and after the decay we have the mass energy of the daughter Z minus 1 and plus 1 C square plus the plus the kinetic energy of the neutrino. Okay, and also this is special about the electron capture, the binding energy of the K shell electron. Okay, so this particular B is the binding energy of the K shell electron. Okay, and why we have to consider this binding energy? Because during the process, the electron from the K shell has to overcome the potential so that it can be released from the orbit. So this binding energy has to be considered. And lastly, the Q value. So the Q value, I use this symbol, is equal to only the kinetic energy of the neutrino, which is equal to the mass energy of the parent minus mass energy of the daughter okay, times the c square minus the binding energy of the cache electron. I skip labeling the parent nucleus with a z and n, and also the daughter nucleus with a z minus 1 and n plus 1 as well, because I don't have enough space here. Okay, so if we check the chart, the live chart, okay, where is the live chart? Okay, okay, this is the live chart, and you can see that for nuclides with same number of proton, same number of z, let's say this line, this particular line, you can see that on the right, uh, there are the uh, on the right there are neutron rich nuclides, and on the left there are the neutron deficient nuclide. So on the right, the nuclides undergo beta minus decay. On the left, the nuclides will undergo electron capture or beta plus decay. So to end this lecture, please do the quiz number 4 and make sure that you send your answer through the Google Classroom. Okay.